Hello, my fellow AMAOEDs and my professor. This is my course project in Symbolic Logic, HUMA102 or HUMA102. I'm Jeffrey A. Diana, Bachelor of Science in Computer Engineering. My chosen topic for this course project is the propositional equivalence. The propositional equivalence. I will discuss to you in different topic about the propositional equivalence in our subject. First is the tautologies, contradictions, and contingencies. Statement that produce proposition with the same truth value as a given compound proposition are used in the construction of mathematical arguments. A tautology is a proposition. First is a tautology from our definition. Is a proposition which always true. For example, our statement P or negation of P. This is always true. Next is contradiction is a proposition. The definition of contradiction. Contradiction is a proposition that is always false. For example, P and negation of P. This is always false. If the statement is true and false, this is always false, except if the statement is both true, the statement also is true. Next definition is contingency. What is contingency? Contingency is a proposition that is neither a tautology nor a contradiction. Either of two. For example, P and or Q implies negation of R. Okay. The proposition P and Q are called logical equivalent if P is logical equivalent to Q is a tautology. The notation P equals to Q denotes that P and Q are logically equivalent. Some textbooks use the notation P logically equivalent to Q to denote the P and Q are logically equivalent. Let us look at my example of a tautology of P or negation of P in the truth table. As you can see in my first statement, P, the given my data is true and false. So let's negate the P, the negation of P. If our P is true, then the negation is false. If our P is false, our negation will be true. So for our solution in our problem, P or negation of P, our answer will be for the first given statement, P, T, and F false for negation of P, our answer is true because this is a tautology. And our symbol here is or. Any statement with true value or both true value will be, or our statement is always true. So true and false is true, and then in the next given data will be false and true, then This one is true. This shows that P or negation of P is true no matter what the truth value of P. So this is our tautology. Okay, I have some example of in the tautology. Let us see our example truth table illustrates below. I have given statement P and Q. For P, I have true, true, false, false, and Q, I have true, false, true, false. Okay, let us okay, wait a minute. Okay, let's return in our slide number 7. Okay. One of the important techniques used in proving theorems is to replace or substitute one proposition by another one that is equivalent to it. In this section, we will list some of basic propositional equivalence and show how they can be used to prove other equivalences. This tautology, called the law of excluded middle, is a direct consequence of our basic assumption that a proposition is a statement that is either true or false. Thus, the logic we will discuss here, so-called Aristotelian logic, might be described as a two-valued logic, and it is the logical basis for the most theory of modern mathematics. At least as it has developed in Western culture, there is, however, a consistent logical system known as constructivist or intuitionistic logic, which does not assume the law of excluded middle. This results in a three-valued logic in which one allows for two propositional equivalence, a third possibility, namely other. In this system, proving that a statement is not true is not the same as proving that it is false. So that indirect proofs we shall soon discuss would not be valid if we are tempted to dismiss this concept. So for our other example, we will answer this proposition P or negation, close parenthesis, P and Q is also a tautology to prove this equation. Let us answer the truth table below. Okay. For our statement P and Q, we have the value true for P and Q. So let's answer this P and Q P and Q, this is both true. So our answer is true. So the next statement, true, the P is true and Q is false. So this is false. This one is false also. And this one is false. This P or Q is a contradiction. For the next, for our next solution in negation of P and Q, let us negate this P and Q. So negation of T or true is false. Negation of false will be true. Negation of false is true. And negation of false is true. And our last problem or our last equation, P or negation of P and Q. So let us check if it is tautology. So P, this is the P, and we will get another equation in this area, the negation of P or and Q. So our P is true and here is false. Our answer is true. Here is true, our second equation, our second statement. True and true is always true. False and true is true. And false and true is always true. As we can see, our equation P or negation of P and Q is a tautology because here in our definition, tautology is a proposition which is always true. Okay. Next topic is the logically equivalent. Proposition R and S are logically equivalent if the statement R is logically equivalent to S is a tautology. If R and S are logically equivalent, we write R is logically equivalent to S. Okay. A second notation often used to mean statements R and S are logically equivalent is R is equivalent to S. You can determine whether compound proposition R and S are logically equivalent by building a single truth table for both propositions and checking to see that they have exactly the same truth table values. Notice the new symbol R logically equivalent to S, which is used to denote the R and S are logically equivalent. This is defined to mean the statement R. Statement R is logically equivalent to S is tautology. In sense, propositional equivalence or equivalences convey similar information when used in a sentence. However, R is logically equivalent to S is generally used to assert that the statement R logically equivalent to S is in fact true, while the statement R is logically equivalent to S alone does not imply any particular truth value. The symbol, this symbol is the preferred shorthand for is equivalent to. This is equivalent I can write because I use mouse only. Is equivalent to. This is the meaning of this symbol. Okay? In my example shows that P implies Q or Q implies P is logically equivalent to P equivalent to Q. Okay? Here is my example. So in my statement P, our value is true, true, false, false, true, true, false, false. And our statement Q, my value is true, true, false, true, false, true, false, true, false. So if P implies Q, our answer will be true because our statement P and Q is the same true. The next one is true and false. So it implies P implies to Q. So this will be false. False, true, this is true. And both false, this is also true. Then we reverse our given Q implies to P. So if Q implies to P, our answer will be this is both true, this is true also. Now this is reverse, false and true. So this will be true. And this true and false, this will be false. And both false, this will be true. So let's answer the next equation. We have P implies Q and Q implies P. So if P implies Q, this one is and P implies Q and Q implies P. What is our answer? If this is and, this is a contradiction. So if we found here is true and this one is true, so if both true, this will be true. Then if we have false and true, this will be false. The next one, true and false, there is false, so this will be false. And both true, this will be true. So the next equation or our next problem will be P is equivalent to Q. Let us see if is equivalent to P is equivalent to Q. So P and Q, this one is both true. So our answer will be true. And this one, true and false. So this is false. False and true, this will be false. And false and false, this will be true. Okay. Examine every possible case in which statement P implies Q. This one, P implies Q, and Q here implies P may not have the same truth values as this one. They doesn't have the same truth values as this statement P is equivalent to Q. Suppose P implies Q and Q implies P is false and P is equivalent to Q is true. So this is false, this is true. There are two possible cases where P implies Q and Q implies P is false. So here, the second statement and the third statement. Namely, P implies Q is false or Q implies P is false. Note that discover the possibility. Both are false since we use the inclusive OR. This one. We use inclusive OR on logic. Assume P, Q is false, then P is true and Q is false. But if this is the case, the P is equivalent to Q is false. Assume Q implies to P is false, then Q is true and P is false. But if this is the case, the P is equivalent to Q is false. So we have another case about this logical equivalence. Suppose P implies Q, this one, and logically or and Q implies P is true, this one, this both statement is true. So P implies Q, this one, and Q implies P is both true. Then P is equivalent to Q is false. If the latter is false, then the P and Q do not have the same truth value. And there are two possible ways which may occur that we address below. Assume P is true and Q is false, then P implies Q is false. So the conjunction also must be false. Assume P is false and Q is true, then Q implies P is false. So the conjunction is also false. We exhausted all the possibilities, so the two propositions must be logically equivalent. Okay. This example illustrates an alternative to using the truth tables to establish the equivalence of two propositions. Alternative proof is obtained by excluding all possible ways in which the propositions may fail to be equivalent. So let us see our given statement in the truth table. The value of P is true, true, false, false, true, false, false. And the Q value is true, false, true, false. So let us negate Q. So negation of Q will be F, true, F. The negation is F. If false, the negation will be true. If true, the negation is false. If false, the negation will be true. Then let us get the equation for P implies Q. So our statement for P implies Q, this is both true. So our truth table will be true. In this one, true and false, this will be false. Then if it is false and true, then true. If both false, will be false. So let us get the negation of P implies Q. So if P implies Q is true, the negation will be false. If P implies Q is false, so this will be true. If P implies Q is true, so our answer will be false. And if P implies Q is true, then our answer is false. So our equation for negation of P implies Q, our answer are false, true, false, false. So let us get the equation P and our logical or negation of Q. So we will get our data here and here. So and or symbol, and symbol. So this is contradiction. So if we have P and P and negation of Q, this will be true and false. So our answer will be false. So P negation of Q is both true. This will be true. And F and F, this will be false. And F and false and true, this will be false. Since the truth values for negation of P implies Q, and P, the logical and negation of Q are exactly the same for all possible combinations of truth values of P and Q, the two propositions are equivalent. So these two propositions are equivalent. Okay. In our last topic, I will discuss to you the importance of logical equivalent. So study carefully what each of these equivalence is saying, with the possible exception of the De Morgan laws. They are fairly straightforward to understand. The main difficulty you might have with this equivalence is remembering their names. So the logical equivalence below are important equivalent that should be memorized in studying the logical equivalences. First, we have the identity loss. So for our identity loss, P logically and is true is equivalent to P. If P and logically or is false, is logically equivalent to P. In our domination loss, the P and logical or is true, it is equivalent to true. If P logical symbol and is false, then this is equivalent to false also. So if it is true, the equivalence is also true. If it is false, and it is logical symbol and is false, then it will be false. Idempotent clause. Our statement or P is logically or to our next statement P. So it is equivalent to P. Or if our statement P is logically and to another statement P, this is also equivalent to P. Double negation law. If we, as we can see, there is a double negation. Negation of open and close parenthesis, negation P. So cancel the double negation or cancel the negative sign. Then this one is equivalent to P. Commutative loss. Commutative loss, this is the example equation. P, logical or symbol Q is equivalent to Q. We will reverse the statement. This is the P or Q is equivalent to Q or P, then vice versa. If it is P and Q, then it is equivalent to Q and P. Then associative law. Associative law, this is our example equation. Open parenthesis P and logical or Q, close parenthesis, then logical symbol or, then the statement R is equals to P, then logical symbol or open parenthesis Q, logical symbol or R, statement R, then close parenthesis. Same as this next equation, open parenthesis P, then let us change this one. This is logical symbol or this is and. Let us change, or this is equivalent to P and open parenthesis Q and R. Distributive loss. This is my favorite. The statement P, logical and. This one, logical and, logical or, sorry. For logical or, open parenthesis Q, and logical and in R, close parenthesis. We will distribute this equation. For example, P, we will distribute this one to this one. Okay, P and Q, this one. Then let us reverse the symbol for this. This is and P and R. Let us get this symbol. Then for another equation, for this one, same as this. So P, Q, P and Q, and P and R. Then let us get this in the middle, the OR symbol. This is the distributive loss. De Morgan loss. The negation of open parenthesis P, statement P, the negation of statement P and Q is equals to negative P. Let us reverse this sign to let us reverse the end sign. The reversal of end sign is the OR sign, or the logically OR. So negation of P or negation of Q. Then for the next statement, negation of P and or Q. So our answer is negation of P here, negation of P. Then reverse this one to end symbol or end, logically end, then negation of Q. This is the De Morgan's law. For absorption loss, if statement P is logically end, open parenthesis, statement P, or logically OR Q, then this is equivalent to P. Then if statement P is logically OR to open parenthesis P and Q, this is equivalent to P. The logical equivalents below are important. That should be memorized also, the implication law. If P implies to Q, this is equivalent to negation of P, logically, or Q. The contrapositive law, if P implies to Q, then is equivalent to negative Q. So let us reverse this one. Then if we reverse this one, the Q, the statement Q becomes negative. So this is negation of Q implies to negation of P. Tautology, the statement P or negation of P is always true. Then contradiction, the statement P and logical end, negation of P is always false. Then the equivalence, if P implies to Q, logically end symbol to Q implies to P. So this is equivalent to P is equivalent to Q. So for the solution, okay. So this study carefully what each of these equivalents is saying. With the possible exceptions of the Morgan laws, they are fairly straightforward to understand. The main difficulty you might have with this equation equivalence is remembering their names. So for our solution in this problem, the negation of P implies to Q is equivalent to double negation is negation of P logically or so statement Q. This will be the implication law. Then the next statement, this one is negation of P implies to Q is equivalent also to, in De Morgan's law, this is double negation P. So double negation P is logically end negation Q. In double negation law, this problem equation, the negation of P implies to Q in double negation law. This is equivalent to P logically and to negation Q. This method is very similar to simplifying an algebraic expression. You are using the basic equivalence in somewhat the same way. You are using rules like this, 2x minus 3x is equals to negative x, or x plus 1 times x minus 3 divided by x minus 3. Our answer is equals to x plus 1. Okay, using the propositional equivalence in the list of important logical equivalences above to prove the P implies to Q logical symbol, or and in negation of Q implies to negative or negation of P. This is a tautology. So here is our last example. Find the disjunctive normal form of open parenthesis negation of P logical or Q close parenthesis logical and negation of R. So let us find the disjunctive normal form of this equation. In our truth table, we have the statement P, Q, and R, and here are our data in our truth table. In our statement P, in truth table, this is the data. We have true, 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 false, true, false, false. Then in our statement Q, we have true, true, false, true, false, true, false, false. In our data R, we have true, false, true, true, false, false, true, false. So let us answer the negation of P in this equation. So the negation of P in this statement P, so if the value is true, so the negation of P will be false. If the value is true, so the negation is false. The value is true, so this is false. If the value is F, so this is T. If the value is T, this is false. If this is false, true, this is false, we have true. If this is false, we have true. Then let us get the negation of R. So the negation of R, this is our given value. If it's true, then this is false. If it is false, this is true. So if it is true, this is false. True, false. This is false. True. This is false. true is true. This is false, and false. This is true. Okay. Now let's get the solution. Negation of P logically or to Q. So let us negation of P. This one we will get here and to Q. So here. So negative P. If it is F and this is tautology. So if it is F and T, this is true. So all the statement that has truth value, this is always true. When it's false, this is false. So F and T, this is true. So this one is false. The true statement is false, so this will be false. So true, this one true, and true is this is true. True and true. False and false, this is false. And true and true, this will be true. True and false, this is true. True and false, this will be true. So in our next equation, open parenthesis, negation of P, or logically or Q is logically N to negation of R. So let us solve with this statement to here, negation of R. So we will get, or we will solve this problem in this two equation. So this one, this is a contradiction. So if our statement is both true, this is our statement is true, and if one of the statement is false, then our statement is all false. So true and false here, true and false. So this will be false. So true and true, this is true. False and false, this is false. So true and false, this is false. False and true, this is false. True and true, this will be true. True and false, this is false, and true, this is true. This disjunctive normal form for negative P or Q to end negation of R. So this is called the disjunctive normal. So false, false, true, true, false, 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 true, true, false, true. Okay. Thank you very much for your listening. I hope you get this topic very clear. Thank you very much.